Hi, I'm Scott Bortoff. I am a researcher at Mitsubishi Electric Research Labs in Cambridge, Massachusetts, and I'm going to give a presentation on some of the research we've done on modeling and control of a Delta robot. So if you're not familiar with Delta robots, here's a movie of one up here. They're interesting closed chain manipulators that are actually very useful for what we're trying to do. And so our sort of long-term goal is to develop robotic technology that enables mechanical assembly of complex things like this cell phone, which consists of many small parts and plugs and things like that. And it turns out that the Delta robot has a number of good properties for that problem, and so we've built one at Merle, and we're developing the control technology for that, which is all based on basically modeling both the robot and the mechanical task here, so all the parts that get assembled. And so it's sort of an exercise in controlling contact and collisions. And it turns out that the mathematics and techniques that we use for modeling and for control can be applied to a lot of other problems, some of them toys and some of them serious problems that we see at Mitsubishi Electric. So for example, in an elevator shaft where you have a rope like this, as the rope comes over the sheave, it comes into and out of contact with the sheave. And that physics can be modeled along with the bending of the rope and, of course, the motion of the cars using the mathematics that we've developed here. Similarly, things like this toy ball maze where the ball rolls in this maze and comes into and out of contact with the rings here is a similar problem where you have loss of contact and recontact. And you're trying to manipulate the maze in order to get the ball into the center. And that's a problem where we've not only modeled it for simulation, but used that model to design a feedback controller to solve the ball maze. Tensegrity problems are also interesting examples where you can apply the same mathematics. Here you have basically two paper clips. This is a little toy example. The top paper clip here is actually hanging from the paper clip on the bottom, and it's stabilized by these four threads that you can see here. And of course, this system has dynamics, and you can analyze those dynamics using the mathematics that we'll talk about. This chain fountain is also a fun toy problem where you have a pile of chain in a little glass beaker here, and if you throw the chain off the edge here and it falls, it forms what's called a chain fountain. It's very interesting dynamics. This can be simulated actually using the same way, where we're basically losing contact with the chain as it comes off the pile. So lots of broad applications here. So what I'll show you here in this movie, which is about 25 minutes long, I hope, is basically some results that I've presented at various conferences over the last couple of years. We'll talk about Delta robots and how they compare with more conventional serial link robots. Derive the kinematics and dynamics of the robot, which is a little bit different than serial link robots. We use the Modelica modeling language at Merle quite a bit for vapor compression systems in particular, but also robotics. It's actually very useful object-oriented language to represent this type of physics. We'll talk a little bit about control, some of the lower level feedback that we've developed for this application, how to model some of these assembly tasks themselves, which is an interesting problem in and of itself, and turns out to be very consistent with how we model the robot. And then here's some of the next steps that we're going to be pursuing, particularly next year, experimentally in our laboratory. So serial link robots, most people are familiar with if you're into robotics at all. Basically, this is an open chain of links, and there's one actuator per joint. The actuators tend to be mounted up in the structure, and so therefore these things tend to be relatively massive, have a lot of inertia, relatively slow compared to a Delta robot. Because you're putting servos up here, you tend to have high gear ratios, which tends to lead to higher friction. And older robots tend to be not backdrivable, although newer ones like this Cobot that Mitsubishi Electric sells is actually. But the point here is that these tend to have very high, relatively speaking, mass and inertia. And so when you're doing a contact type of operation, when you have a collision, these can impart a lot of mass or momentum into whatever you're trying to assemble, and that can cause some damage. Now, if you look at a delta robot, because the servos are all mounted here at the base, which is inverted in this example, these links tend to be very lightweight, low mass, and moreover, because you've got unactuated universal joints here and here, there's no torque on this link, the distal link, and so there's very little bending of these joints and links. And so this tends to be very precisely mechanical, very good repeatability. Also, of course, very low inertia, very low mass. That means they can be fast, but it also means that when we do have a contact, we're going to impart less momentum into whatever we're trying to control. And so that's the main benefit of this type of robot. They also are very strong, very high payload to mass ratio. In fact, this is a robot that's offered by Codian, one of our partners. It can have a payload of up to 100 kilograms, although it might not look like it, and do a maximum of 250 operations per minute. So these things are very fast. But our primary interest in them is the low impedance that we can achieve, which is in part due to the low mass and in part due to the control that we'll talk about later. So now if we talk about the kinematics and dynamics, there's some interesting differences. So the forward kinematics of a serial link robot can be written explicitly. There's a formula you can derive depending on what type of robot you're looking at. So it's analytic, it's closed form. The inverse kinematics, usually you cannot do that. But because I can express the forward kinematics deriving the Jacobian and the dynamics is a relatively straightforward exercise, that's been well known for many decades. Now, the delta robot is what's called a closed kinematic chain. And so the implication of that is that the forward kinematics are actually an implicit set of nonlinear equations, and they cannot be solved in closed form. And so that has implications. One of them is the Jacobians. It turns out that there are two that are of interest, can't be expressed in, well, at least one of them can't be expressed in closed form. And that has implications on the dynamics. The dynamics we can express explicitly if we adopt a differential algebraic equation framework, and so that's what we're going to do. Interestingly enough, for a lot of these closed chain manipulators, like the delta robot, the inverse kinematics can be expressed explicitly. You can actually write down closed form expressions for the inverse kinematics, in other words, the map from where this wrist flange or end effector is in Cartesian space back to the measured joint angles, which are these servomotor angles. It's just a rather cumbersome exercise in trigonometry. Okay, so it turns out that most delta robots today are used for relatively simple pick-and-place type of operations, and that needs very simple control. And in fact, that control doesn't need to know anything about the dynamics of the robot. We basically close PID feedback loops around each servo. That PID tends to be software that's already inside the inverter, so you don't need any extra hardware. We usually want to compute the inverse kinematics, so we can do some sort of path and trajectory planning, but that's relatively straightforward. And so here's a sort of typical example of how you might use a delta robot. Whoops, here we're sorting some pancakes. Well, that's fine. We'll skip the video. So our primary application is, again, we want to do assembly with these types of things. And so what we're going to want to do is derive feedback control laws based on a dynamic model for which we can modify the robot's impedance to get very soft contact. And so the dynamics that we've derived are based on a differential algebraic model. We published it a couple of years ago. Basically, very simple idea. We write down the kinematics of each individual arm, assuming they're not connected at all here. So those are open chains. We can derive the dynamics of each one of those. And so we have a joint here at the motor and a universal joint here. And we derive a set of dynamic equations from that in a straightforward way. And then what you do is augment that. We basically augment the Lagrangian with the holonomic constraint that all 6 of these links need to come together. And so there are 6 nonlinear equations here that are added to this set of robot dynamics. We end up with 24 equations, 24 states. 6 of the states are these Lagrange multipliers, so they're algebraic constraints. And so this is a completely legitimate index 3 differential algebraic equation model of the robot. It has nice properties, so it has no singularities. It can be you can easily simulate the robot through its sometimes very strange kinematic singularities. And usually we want to reduce this index to 1 or 0 so that basically simulators, simulation algorithms, and control theory works a little better. And so we do that in different ways. Here we're going to replace this constraint with a linear combination of its first two derivatives with respect to time. And now I have an index 1 DIE. It's global, no singularities, and actually is very useful for deriving different types of control algorithms. Now, it turns out that most serial link robots, you basically compute the Jacobian of the forward kinematics, and that's the Jacobian of the manipulator, which is the map between forces applied here and torques applied here at the wrist back to forces and torques at the joints. But for the Delta robot, not all the joints are actuated. It turns out there are two Jacobians that we're interested in. The first one is only for simulation, and what it is, it's the map from this force to all of the joints, and so we can use this in a simulation. It's not useful for control. We need a different Jacobian for that. Talk about that on the next slide. This is a relatively straightforward thing to derive because it's just dependent on the forward kinematics of each arm independently, which is an open chain. And so there are actually many different formulations for this, but we can compute this as basically a simple derivative, the Jacobian of each forward kinematic of each arm. And this is what's important. It's a closed form analytic formula. And so we can use this in simulation together with this dynamic model, and we get a smooth, again, singularity-free model throughout the entire workspace that works very well with index 1 DAE solvers. Now for control, we need something a little different. Again, the Jacobian here is the map between forces and torques applied at the end effector or wrist flange here, back to just the servomotor torques. And so if we want to apply a torque or a force to an object, this is the torques that we apply to the motors. Now by construction, torques applied to this wrist flange are just absorbed by the structure, which is another nice benefit of the Delta robot. It decouples forces and torques here, and that will simplify the overall control. But this is what we call the control Jacobian. So this is the Jacobian of the forward kinematics, which again is not solvable. So we need to use some sort of numerical solution or algorithm to compute that. So here we're using Newton's method to solve the forward kinematics, and then it's sort of a application of the implicit function theorem a few times here, derive these equations, and we can then compute this Jacobian numerically. And so when we're deriving control laws, which will be implemented in discrete time, then this is what's used there. This is not used in any sort of simulation of the robot, again, because it needs to be computed algorithmically, and so it has a termination condition here. This does. And so, in fact, it means that this is computed not continuously, and that will cause problems with any sort of index 1 solver. So we use the previous one for simulation and this one for control. So we make a lot of use of the Modelica language here at Merle. The Modelica language is basically it's an open source language intended to model and primarily for simulation of multi-physical heterogeneous types of systems. So, sort of think of systems of systems. What's interesting about it is an a-causal language. It's an equation-based language. And that means that when we have physics equations, like this one here, these are 5 equations that describe the motion of a pendulum, but in Cartesian space, so they look a little funny. This is, again, an index 3 differential algebraic equation. We can transcribe that directly into the language. And the important thing here is here's mass times acceleration equals a force. The equal sign here in this language means equals as it does in physics. It's a constraint between variables. It does not mean assignment as it does in many computer languages. And so it allows us to express physics very naturally, and it's got a lot of object-oriented structures that are useful in creating libraries and different types of models, particularly in robotics, multi-body systems, and thermal fluid systems. So this is actually the Modelica model of the entire robot. What's nice is you can express it on a single page, so you can easily check to see if it's correct. Basically, you declare a bunch of variables and declare actually arms, the arm dynamics. Those are not shown here, so we declare 3 of them, arm 1, arm 2, and arm 3. And then we just, here is the holonomic constraint with the index reduction set of equations. And the rest of these are just to derive that virtual Jacobian so we can simulate the effects of force. So we make use of a lot of object orientation here. We basically start with the arm kinetics, which are not shown. They're a different file. We extend that to derive the arm dynamics, instantiate that 3 times in the robot dynamics. And then, in fact, we can instantiate many different robots, but this robot in a larger task space and model the task itself. And so that's the important thing, is the language and the mathematics extend from the robot all the way into the task that we're trying to accomplish. Now, of course, we use these models for simulation, but we also use them for dynamic analysis and control design. Here's an interesting result. It turns out that the Delta robot is actually open-loop unstable in a large volume of its workspace. And so here are actually 2 configurations. This is sort of the home configuration, and here the first proximal link is commanded to be 0 degrees. And in this configuration, actually, if you were to linearize it, you'll find that there's 1 mode in the right-half plane. And that's a bit surprising, perhaps, but if you were to actually apply the constant torque that holds the robot at this place, you would see that it actually will fold up and smash into itself. And so that has implications for what we're trying to do, because if you have an open-loop unstable system, then there's a lower limit on what the feedback gain needs to be in order to stabilize it. However, in a lot of contact applications, we would like to reduce the feedback gains in some cases to 0, so we get very soft contact. And so this is something that one needs to consider when you're actually designing a feedback controller. Another interesting thing about these robots, I find it rather amusing, is that they have different types of kinematic singularities. So I'll give you an example of one here. Of course, when each of these links is straightened out and it's basically fully extended, that's a kinematic singularity. But another one happens when all 6 of these distal links become parallel. And so we can actually here use our Modelica model and just wrap PID feedback loops around each servo and command them to the angle that drives each of these in parallel. And so we'll see exactly what happens in this animation. So here we're seeing the servo motor ramp up and move them into position. And what happens is, when all 3 of these become parallel, the robot enters into a singularity and it becomes essentially a spherical pendulum. So if we hit it with a force down here, you'll see it just goes back and forth. Here's the simulation of that. So there are really 2 points here. One is that the model works everywhere. It's global, it's singularity free as a model. If we were to express the dynamics here in terms of just the variables for the motors, which I call y, you would find that that model has a singularity, and you would have to do some sort of switching to get around it. The other thing is, of course, the control system needs to avoid this configuration because it's sort of useless as a robotic manipulator. So let's talk about assembly control. Basically, the strategy is very similar to any type of robotic application. We have sort of a stack of software and hardware. So at the lowest level, you have your hardware and then sort of inner loop control. In this case, we're going to linearize the robot dynamics and then have an outer loop here where we can adjust the feedback gains in order to modify the robot impedance depending on what it's doing. And then an outer loop there for planning the path and trajectories. And then finally, at the highest level, we have some kind of a task planning. And so in terms of where we are here, of course, we've built this in our laboratory. The inner loop control is essentially finished, as is the outer loop control. We've done a lot of path and trajectory planning. And we're now designing different behaviors. We'll talk about one of those later. These behaviors are a mix of finite state machines and in some cases, optimization-based control. And then these behaviors get organized into larger tasks. So talk about the inner loop control a little bit. It's a little bit more complicated than it would be for a serial link robot because we've basically modeled it as a higher dimensional system, so it's embedded in an 18-dimensional space when it's expressed in index 1 form. The first step is we have to basically cancel out the effect of gravity. So if we look at the dynamics, here's the inertia. These are the Coriolis and centripetal forces. this is damping, and this is the gravity force. And so we're going to use the torques to cancel out the gravity force. And essentially, that cannot be done, again, explicitly. These are implicit equations. And so we basically have to solve this 9x9 system of linear equations in real time. So we solve it basically for this control torque. We also get the Lagrangians out of that if we want to use that in some other control context. We end up with this system here, and then again, this is in a higher dimensional space. So what we need to do is basically separate the measured variables, which are these servo motor angles, from the unmeasured variables, which are the joints here. So we need to eliminate those from the dynamics, and that's what this step is here. And we end up with this equation, so it's starting to look a little more linear. And then depending on which coordinate system you want to linearize it in, you get these two control laws. So the more useful one is the second one here, where it's actually linearized in the task coordinates. And so to implement this, we need to compute this effective inertia matrix and also this inverse Jacobian, which is the control Jacobian we saw earlier. This feedback control will, of course, have singularities. You cannot move the robot through that kinematic singularity we saw earlier, or this inertia matrix will actually go singular at some point. Actually, what happens is this map goes singular. And so we need to avoid that during the operation of the robot. Now, we actually implement all of our control algorithms in the Modelica language natively. So this has a synchronous library and also a devices drivers library. The former allows us to implement the correct sample data behavior, and the latter allows us to run this controller in real time, so we can do desktop simulations in real time. We can also do our experiments in real time. We'll talk about that on the next slide. And so here, these are the continuous time dynamics of the Delta robot. It's actually in contact with a Lego brick. In this example, we have the forward kinematics, which need to be computed algorithmically, our gravity feedback, and then this is the feedback linearizing control in the y coordinates in this example. And here's an example where it's just following a trajectory that's generated by the joystick. And you see you get perfect tracking because there's no model uncertainty. Of course, this is a simulation. But this is the important thing. We can then take that controller, which is implemented in Modelica. We basically strip out the continuous time model. We interface it with some real-time software we've developed, recompile this thing, which is a button push, and we can run exactly the same experiment now using our actual Delta robot hardware, which is shown down here. Here's a simple example where it's doing the same sort of trajectory tracking. Of course, the tracking here is poorer because we do have a little bit of model uncertainty. And here we've really reduced the gains a lot to show off that model uncertainty. So in a real application, we would want to reduce these gains quite a bit, again, when we want to do the SoftContact that we'll talk about in a little bit. So let's talk about this. There are sort of two aspects to achieving this SoftContact by impedance control. And so the first one is what we're going to do is basically reduce the feedback gain. In this case, we'll just reduce the P gain in the outer loop all the way to 0 as it comes into contact. And the reason we can reduce it all the way to 0 is because we've feedback linearized it here and compensated the effect of gravity that actually causes that open loop instability. And so the outer loop now can be actually tuned or detuned all the way down to 0. Here what we're trying to do is we've got a few games that we play, but one of them is to play this game called Jenga. So in Jenga you basically pile these wooden blocks on top of each other like this, and the idea is to push out one of these one player at a time. The one you push out you need to stack on the top, and so you keep building this tower up until it falls, and whoever knocks it over is, of course, the loser. These are interesting games. The Jenga blocks are actually very precisely machined, so there's a little bit of variance in their height. If these were all the same height, of course, the game wouldn't work. Because there is a little bit of variance, there's always one or two that are loose that you can push out, but of course you need to do it very softly. And so here the robot is actually coming in contact with the block, one of the blocks. You basically approach it at low velocity, detune the gain to 0, and then when you actually do come in contact, it's very soft force. So here it's 5 times 10 to the minus 5th newtons, which is sufficiently soft so it doesn't disturb this in the wrong way. So that's half the game. The other half of the game is that we can actually do better than that So in a lot of cases, we have a little bit of uncertainty as to where an object is in space. And when we try to pick it up with one of these parallel grippers, so here the fingers of the gripper are in green, and the robot mass is just represented here in red. Here's a Jenga block, for example. If you were to try to pick this up, what's going to happen is this is going to slide over and you're going to lose the game. In an industrial application, there's position uncertainty, and you really want to be robust with respect to that. We don't want to impart any momentum or force, or as little as possible, onto that block. And so here we're using some tactile sensors that are mounted on the inside fingers, and we just derive a very simple feedback controller. We take the difference between the left and the right, feed the difference back to the outer loop control, that feedback linearizing control, that controls the robot horizontal position. And what that achieves in the frequency domain is it greatly reduces the impedance, which is the gain here. Here it's the gain from finger velocity to the contact force, or from finger velocity to block velocity. And so you can see that in the frequency band where the control is effective, you're making the robot softer. You're going to impart less energy to it, the object that you're trying to pick up in this case. And what's interesting about this is a sort of systems point of view. We're trying to reduce impedance. There's no switching or if-then-else or signal-based type thinking here. This is purely system type thinking that is intended to reduce the robot impedance. And as it picks up this block, there is no switching or anything like that. We can achieve a grasp that's very soft without any sort of hybrid logic, which is very important because it's difficult to tune that in practice. So I'll show you an animation. This is a bit of a close-up here. Basically, for the first animation, we're going to, these yellow things are the touch sensors. We're going to ignore that. There's no feedback. This is what a robot would do. After I've detuned its position gain, so it's as soft as it can be. I'm using a low mass and robot. However, this block is very low mass itself, and so if we try to pick that up, well, what's going to happen as the two fingers come together? Of course, they're going to move the block, which is undesirable. And so we'll show that again. And sort of here's the graph of that. You can see the block moves in this case in an undesirable way. And so next what we're going to do is turn on the feedback controller. So basically now we're using the tactile sensors, feeding that back to the robot position control. And what you'll see is we can achieve a very low amount of motion in that block. So here's sort of the simulation. But again, this is derived using a systems derivation. There's no switching as we pick this thing up. And in fact, after we pick it up, we can also put it down. And as we put it down, also impart very little velocity using the same type of feedback. So regarding modeling tasks, there's an awful lot of previous work on this subject, particularly the last 20 years or so out of the computer graphics community. So there are all sorts of these so-called physics packages, Bullet, PhysX, Gazebo, et cetera, et cetera. So honestly, what these things do is they basically represent contact and collisions as very large, in some cases, nonlinear complementary problems, which are approximated by linear complementary problems, LCPs. These can be solved as QP problems, and essentially they all work the same way. You discretize the dynamics, you solve a constrained QP at each discrete step. There are very efficient solvers for that, of course. And really the only purpose of these things is to simulate. And so it's difficult to use these models in any sort of mathematical way for model-based control design, for example, to analyze the dynamics because the solvers are all mixed together with the model itself. And there are also issues with these solvers. So basically the success criteria for these is, does the simulation look good? But in fact, energy is not necessarily conserved. There's a lot of tolerances that need to be tuning. Here's a simulation of a very large number of blocks that are being dropped onto a table, and some of them bounce higher than others. Now that's what you would expect if you were actually doing that experiment on your desk. But since all these blocks are identical, the simulation should actually be the same for each block, and it's not. This is most likely an artifact of the solver, not necessarily the physics. And so we're thinking about different ways to model contact and collisions in ways that are consistent with the way we model the dynamics of the robot itself. And this is actually one idea where we have both the same sort of structure of models. So you have basically a constrained dynamical system. The constraint here is the Lagrangian, which is the force between objects. And we add to this state machine that basically dictates whether or not this Lagrange multiplier is active or not. So this is another way to sort of think about how to solve a nonlinear complementary problem. Only instead of solving it as an optimization problem, we solve it as a dynamical system using DAE solvers. And so there's a little bit of math here about how to represent elastic collisions and how to design this finite state machine so it's well behaved. But it tends to work pretty well for low-dimensional systems. And here's sort of a toy example. Again, it's this ball maze game. This has been used in vision research at Merle. The idea here is you want to tip-tilt this ball maze and get the marble into the center. And so we're going to cheat a little bit to solve this game. And instead of doing tip-tilt, what we're going to do is angle the maze up at a certain angle, and then we're going to rotate it about its central axis. That's the only degree of freedom that we're going to do. So here's the central axis. We're just going to rotate it. And essentially what we're going to do is stabilize the ball against one of these rings using feedback. So we need to measure the ball position. That's the only measurement we require here. And then we're going to rotate the maze underneath the ball until the ball just falls into the center. So the point here is we can derive the dynamics just like we did earlier for the robot. There's some constraints. There's some finite state machine here to represent the either contact with a ring or when it's falling through a ring, you're in non-contact. And so it switches back and forth between there. But the point is that now we have a mathematical model of this, and we can use that mathematical model to design feedback controllers to stabilize the ball. So basically the control problem is relatively elementary. We just can use a root locus here and 2 lead filters. First to stabilize the ball against a ring, so that's what this root locus is, and that's what this feedback loop is. And then the second one is you need to stabilize the actual maze. There's a pole that's left here at the origin that you need to move away. And so we can tune all of this using the model, implement this feedback controller in our Modelica language, and then simulate the ball maze. And so here's some fun simulations where you can basically start the ball from outside the maze. It falls onto this because of gravity. Again, this thing's tipped up. And then we rotate the maze back and forth. Here it's rotating back and forth as the ball just sort of falls and eventually reaches the center. And so anyway, this is a good example of how you can use a consistent mathematics with the robot, or in this case, collisions, in order to derive a controller and also simulate it. So again, we want that consistency among the different formats of the model. So I'll finish up here. What we're doing with our robot next is basically we've begun to sort of solve a bunch of toy problems. And so one of them is assembling Lego. Robots have done that before, but they have a perfect knowledge of the geometry, and they tend to use larger Legos. Standard Legos, they're very precisely machined. They have very high tolerances, very similar to factory automation type of applications. And there's also a pretty high ratio between the impedances that you need to successfully put something like this together. The Jenga game is also another fun game to play for the robot, again, because you need to push these out very softly and grasp them, subject to some uncertainty in their position. So in order to do this, we've actually developed a 6th degree of freedom wrist that we will add to the robot very soon. So this is basically a Go platform. Some people call this a Stewart platform, but actually it was invented by a gentleman named Go. So this provides an additional 6 degrees of freedom added to the 3 it already has. We get 9. And then the gripper, of course, has its own. So we have a system with a total of 10 or 11 degrees of freedom, depending on how this gripper is operated. Turns out that the Go platform can be modeled and controlled in exactly the same way that Delta Robot can be. So we use the same DAE formalism. We can linearize its dynamics. You can represent this together with the Delta Robot as a uniform system. Of course, modeling this contact physics here is also consistent. So we can do both simulations and experiments of the whole thing. And so in 2021, we'll be doing a lot of these types of demonstrations, hopefully, um, and continuing to develop out our control library. So thank you very much for your attention. And if you have any questions or comments, please feel free to contact me. My email's on the first slide. Thanks a lot.